Hey everyone, and welcome to This Explainer. I'm really thrilled you're joining us today because, well, we're going to unpack something absolutely fascinating. Have you ever wondered what actually makes your internet faster? Not just the physical router sitting on your desk, but the invisible underlying tech that powers our cell towers, 5G networks, and the upcoming super fast Wi-Fi 7? Well, today we're decoding a truly groundbreaking engineering architecture that solves one of the biggest bottlenecks in modern telecommunications. It's called an SNR-improved Delta-Sigma digitization scheme. Okay, I know that sounds incredibly complex, right? But don't worry, we're going to break the whole shebang down piece by piece until this invisible engineering makes perfect sense.
Okay, let's dive into this. Every single day, the global volume of data usage is just exploding. Between 4K streaming, massive multiplayer gaming, and remote work, we are all demanding higher and higher speeds. But here's the thing. The physical radio frequencies and fiber optic cables carrying all that data, they have limits. They can literally only handle so much traffic before the signals get completely garbled. So, the multi-billion-dollar question looking ahead is this. How will our networks handle the massive data demands of tomorrow without having to lay down entirely new physical infrastructure everywhere?
Here is our agenda for today. 1. The data traffic jam. 2. Signal noise, the enemy of data. 3. A twofold solution, dual modulators. 4. Simulation and testing, real-world performance. And 5. Future connectivity, what this means.
Section 1. The data traffic jam. Current bottlenecks.
So to really grasp the solution, we first need to understand what's happening inside the networks we rely on right now. Our current mobile front-haul networks, those high-speed links connecting cellular base stations to the core network, are basically experiencing a massive digital traffic jam. Current generation Wi-Fi 6 uses a standard called 1024 QAM, but the upcoming Wi-Fi 7, which promises ridiculous speeds, demands 4096 QAM or even higher just to expand its data capacity. The problem? Well, our current analog and digital architectures really struggle to process signals dense, without the data just falling apart.
Let's quickly define that acronym so we're all on the exact same page. QAM stands for Quadrature Amplitude Modulation. You absolutely don't need an engineering degree to understand this. Just think of QAM as a technique used to pack more data bits into a single transmitted symbol. If a data stream is like a highway, higher QAM is like stacking cars on top of each other so you can fit way more traffic into the exact same lane. It's incredibly efficient, for sure, but it requires absolute precision. If the road is bumpy, those stacked cars are going to crash.
Section 2. Signal noise. The enemy of data.
Those bumps in the road I just mentioned? In telecommunications, that's known as noise, and it is the absolute enemy of high-capacity data transmission. The primary metric engineers use to talk about this is SNR, or signal-to-noise ratio. This is simply the measure of a desired signal's strength relative to the background noise. Basically, higher is better. When you're trying to decode those incredibly dense stacked data symbols of high-order QAM, you need a crystal-clear signal. Traditional network setups actually waste a lot of their spectrum resources just trying to overpower and overcome this background noise. Now, what's really interesting about this slide is the sheer scale of the improvement. The traditional method used in these networks is a 2-bit Delta-Sigma quantization scheme, but because of in-band noise, its SNR is capped at about 40 decibels. That means the absolute best it can support is 1024 QAM. It just hits a hard ceiling. But this new architecture we're analyzing today, the twofold Delta-Sigma scheme, literally shatters that ceiling, hitting an SNR of 57.7 decibels. That enables a staggering 65,536 QAM. Guys, that is a completely different universe of data capacity. Section 3. A twofold solution. Dual modulators.
So how exactly did they pull off this massive leap in performance? The paper details a distributed MASH-like structure with dual quantizers, which, can sound pretty intimidating. But honestly, just think of it like noise-canceling headphones for your internet data. When you wear noise-canceling headphones on a loud airplane, a little microphone listens to the engine noise, and the headphones generate an inverse sound wave to cancel it out, leaving you with just your music. This new Delta-Sigma architecture basically does the exact same thing, just to the quantitation noise inside your data signal. Let's walk through the actual steps of this virtual noise cancellation process. Step 1, the main desired signal enters the first Delta-Sigma modulator, let's call it DSM-1, which quantizes it or converts it into a digital sequence. But this process naturally creates quantitation noise. So, moving to step 2, the system cleverly uses a filter to extract just that specific in-band noise.
Step 3 is where the real magic happens. A second modulator, DSM-2, processes that extracted noise. Finally, in step 4, it uses a technique called gray coding to combine the clean signal and the processed noise into a neat 4-level format for transmission. Later, at the receiver side, the system uses that noise profile to completely cancel out the interference, leaving an incredibly pure signal. Section 4. Simulation and testing, real-world performance. Now, the theory is brilliant, but how does it actually hold up? Because in engineering, it only matters if the math translates to reality, right? The researchers ran extensive MATLAB simulations to test different setups. The key variable here is the oversampling rate, or OSR. Basically, this is how fast the system samples the analog wave compared to its bandwidth. If the OSR is too low, you get higher bandwidth but lower signal clarity. If it's too high, your clarity is amazing, but your data capacity just drops. Notice that middle row? An OSR of 8 is the absolute sweet spot. It provides a phenomenal balance, maintaining a wide 625 megahertz bandwidth while achieving that incredibly clean 57.7 decibels of SNR.
So the crucial point is this massive 17.7 decibel jump. That is the exact measured improvement of this new dual modulator scheme over the traditional 2-bit OFDM scheme when tested at that sweet spot OSR of 8. In the world of telecommunications, a 17.7 decibel jump isn't just a tiny incremental upgrade. It is a monumental leap in signal clarity.
And this brilliantly illustrates the ultimate result of that clean signal. Because the background noise is virtually eliminated, the experimental setup successfully processed an ultra-high 65,536 QAM signal at a sampling rate of 1.25 gigasamples per second. Just to put that into perspective, going from 1,024 QAM to 65,536 QAM means you're packing exponentially more data into the exact same slice of spectrum. It effectively increases the capacity per channel by an astonishing 60%. Section 5. Future connectivity. What this means. So what does this invisible math actually translate to for the networks we interact with every single day? Well, the most exciting part of this explainer is that this isn't just a whiteboard theory. The researchers successfully transmitted this massive 65,536 QAM signal over 20 kilometers of standard single-mode fiber optic cable. They also proved it's robust across different frequency bands by successfully testing a 3.5 gigahertz wireless signal. And perhaps most importantly, they proved this highly complex process can be run using accessible, low-cost commercial FPGA digital devices. It's scalable, it's cost-effective, and it fits neatly into the 5G and Wi-Fi networks we're currently building out. We are entering an era where the data we consume, from augmented reality to real-time AI processing, demands networks of absolutely unprecedented size and speed. By treating signal noise not as an obstacle to be overpowered, but as a giant puzzle to be canceled out from within, this Delta-Sigma architecture opens a massive new lane on the digital highway. So I'll leave you with this. With software architecture this brilliant, as the physical hardware inevitably catches up, just how fast could our digital world become? Thanks so much for learning with me today. Keep asking questions, and I'll see you in the next explainer.